Welcome to the world of vibration.
Oh, finally. We are moving on to Chapter 5. And judging by the little girl playing the trumpet in the corner, and that speaker blasting out particles, we are getting loud today. We are talking about sound.
We certainly are. But Sarah, before we get to the music, look at that speaker on the left. It's not just making noise, it's doing something very specific to the air.
It looks like it's pushing the dots? Like it's shoving the air forward?
Exactly. That is the fundamental secret of this entire chapter. Sound isn't just magic that hits your ears. It is a mechanical wave. That speaker is physically shoving air molecules, creating squished-together sections called compressions, and spread-out sections called rarefactions.
So it's like a domino effect?
Precisely. We call that a longitudinal wave. In this lecture, we are going to break down exactly how that energy travels. And it's not just about air, Sarah. We're going to calculate the speed of sound through water, and even through solid steel.
Wait, sound travels through steel?
Oh, much faster than it travels through air. We'll get to the math of that soon. But looking back at our trumpet player there, she introduces another huge concept, pitch. Why does a trumpet sound different than a tuba?
Because the notes are higher?
Right, which means the frequency is higher. We're going to learn how wavelength and frequency dance together. And we won't stop at human hearing. We are going to talk about sounds you can't hear, infrasound, which elephants use to talk across the savannah.
No way. Elephants have secret conversations?
They do. And on the other end, we have ultrasound, which bats use to hunt moths in the dark. It is an incredible spectrum.
Okay, I'm hooked. But what about when things move? Like when a police car zooms by?
That is the grand finale of this chapter, the Doppler Effect. It explains why the pitch of a siren drops as it passes you. It's a phenomenon that affects everything from ambulance sirens to the light coming from distant galaxies.
Wow. From trumpets to galaxies. I am ready to start. Where do we begin?
We begin with the wave itself. Let's dive in. Transition to the mechanics of sound. Consider this: you are holding one end of a stretched-out slinky, and you sharply shove your hand forward and pull it back.
Okay, I can picture that. I'm not waving it up and down like a snake, right? I'm shoving it straight forward?
Exactly. You are pushing along the same line the spring creates. This generates what we call a longitudinal wave. Look at the coil diagram there. See how some parts are squashed together tight, and others are stretched apart?
Yeah, it looks like a pulse traveling down the line. But how does that connect to me speaking to you right now?
Because air is just a giant, invisible slinky. When I speak, my vocal cords push against the air molecules. Look at that block of dots, image A.
It looks like TV static, but I see vertical bands that are darker.
Those darker bands are where the air molecules are jammed together. We call that a compression. The lighter, emptier spaces between them? That is a rarefaction.
So sound isn't actually a curvy line flying through the air? It's just a shoving?
Precisely. It is a mechanical disturbance of pressure. But, and here is the trick, we draw it as a curvy line. Look at the graphs labeled B and C right below the dots.
Okay, graph B says density variation. The curve goes up whenever it hits those dark, squashed bands of dots.
Correct. Where the dots are bunched, density is high, so the sine wave peaks. Now, look at graph C.
Pressure variation. The curve looks identical to the density one.
Because they are physically linked. In regions where the air density is high, the pressure is naturally high. So even though the air is just shoving back and forth longitudinally, we plot that pressure change as this beautiful, smooth sine wave.
I get it. The wave shape isn't the motion of the air, it's a map of the pressure squeezing and releasing.
You've got it. That regular, rhythmic squeeze is what your ear detects as a tone. The speed of sound. Look here, at the equation in the top right corner. V equals lambda times F. This is the golden rule for wave mechanics.
I see the V, which stands for velocity, right? But what are those notes next to wavelength and frequency? One says increase, and the other says decrease.
That creates a seesaw effect. C, for a specific medium, the speed of sound, V, is basically a constant speed limit. It creates a balance. If you increase the frequency, the wavelength must decrease to keep that speed steady.
Oh. So you cannot just make the wave go faster by shouting at a higher pitch?
Exactly. You just make shorter waves. Now, look at the red box on the left. In standard air at 20 degrees Celsius, that speed limit is 343 meters per second.
About 770 miles per hour. That is fast, but look at the table on the right side. It lists aluminum at 6,420 meters per second.
Isn't that wild? That is nearly 20 times faster than in air.
But why? I thought air was easier to move through than solid metal.
It is counterintuitive. Look at the bottom bullet point on the left. It says, the stiffer the material, the faster the sound wave. Think of the atoms in steel or aluminum as being connected by really stiff springs.
Okay, I am imagining stiff springs.
When one atom moves, it snaps the next one forward instantly because the bond is so stiff. In squishy materials like plastic, which you can see in the table is only 2,680, the energy transfer lags a bit.
I see plastic is way slower than steel, but still faster than water. And water is faster than air.
Right. Air is just loose molecules bouncing around. Speaking of bouncing, look at the bottom of that table. Compare air at 20 degrees versus air at 0 degrees.
The 20-degree air is faster. 343 versus 331.
Because heat is just motion. Hotter molecules zip around faster, so they can crash into their neighbors quicker to pass the sound along.
So if I want my voice to reach you faster, I should turn up the thermostat?
Technically, yes. Though you might just get sweaty before you get heard. Now, let's turn our attention to the fascinating limits of our own senses, specifically regarding the frequency of sound waves. We tend to think that if we can't hear a sound, it simply doesn't exist. But biologically, humans are actually quite limited. Our ears can only detect frequencies between 20 Hz on the low end and 20,000 Hz on the high end.
That sounds like a pretty wide range, but I'm guessing in the grand scheme of physics, it's actually narrow?
Exactly. It is a tiny slice of the pie. Anything above that 20,000 Hz ceiling is what we classify as ultrasonic, and anything below 20 Hz is infrasonic. Just because we can't hear them doesn't mean the air isn't filled with these noises.
Like the image on the right. That looks like a strobe motion shot of a bat, right?
Precisely. This is a perfect visualization of ultrasound in nature. Bats and dolphins are the masters of this. That bat isn't just flying in the dark, it is producing ultrasound almost continuously. It listens for the echoes bouncing off objects to navigate.
Echolocation. So they are essentially seeing with sound frequencies that we are totally deaf to.
Correct. But here is where it gets really dramatic. Look at the bottom right of that strobe sequence. You see the moth?
Yeah, it looks like it is about to become dinner.
Not necessarily. This slide mentions a fascinating defense mechanism. Evolution works both ways. Some insects, like certain moths and praying mantises, have actually evolved the ability to hear those ultrasonic clicks of a hunting bat.
Wait, so they are tuning into the predator's frequency?
They are interception experts. When they detect that specific ultrasonic frequency, they take immediate evasive action. Some moths will instantly fold their wings and drop into a freefall dive toward the ground to vanish from the bat's sonar.
It is like an invisible aerial dogfight happening right above our heads.
It is. And we are completely oblivious to it, simply because our ears stop working at 20,000 Hz. Here is a fascinating point about the duality of sound waves. We often think of sound as something we just hear, like music or speech. But if you look at these two medical applications, you see sound behaving as both a gentle painter and a heavy sledgehammer.
A sledgehammer? I'm looking at the top image, and that is definitely a baby in the womb. That seems pretty gentle to me.
Exactly, that is the gentle side. This is ultrasound imaging. It relies on the same principle as a bat finding a moth in the dark. We send bursts of high-frequency sound ultrasound into the body.
And then you just listen?
We listen for the echo. When that sound wave hits a boundary, like the change from fluid to the baby's soft tissue, it bounces back. By measuring the precise time delay of those echoes, the computer calculates the depth and maps out the hidden structures. It's the technological equivalent of echolocation.
So it's basically drawing a map based on how long it takes the sound to return. But then, look at the bottom photo. That machine looks completely different. It looks like a sci-fi cannon.
In a way, it is. That is shockwave lithotripsy, or SWL. This is where we stop using sound just to see, and start using it to destroy.
Destroy? The text says it's for kidney stones?
Precisely. Sound waves carry energy. If you concentrate that energy, just like focusing sunlight with a magnifying glass, you can create intense pressure. In this machine, we focus an intense beam of ultrasound directly onto a kidney stone inside a patient.
It says here 1,000 to 3,000 pulses at 23 joules per pulse. That sounds like a lot of energy.
It is immense. Imagine tapping a rock 3,000 times with an invisible acoustic hammer. The sound waves pass harmlessly through the soft skin and muscle, but when they converge on the hard stone, the energy spikes.
And the stone just shatters?
It fractures into tiny pieces, sand, essentially, that the body can pass naturally. No scalpel, no incision. Just the raw mechanical power of sound waves doing the work.
That is wild. So one machine whispers to see a new life, and the other shouts to smash rocks.
Physics in action, Sarah. Physics in action. Let's dig a little deeper into the world of sounds that are actually too low for us to hear. What we are looking at here is the realm of infrasound.
Okay, I see the word infrasound in big letters, and I see these majestic whales swimming in the ocean. But if we can't hear it, how do we know it is happening?
That is the fascinating part. Infrasound refers to frequencies below 20 Hz. Now, humans essentially stop hearing pitch at that level, but we still detect it. We feel it as a vibration. Think of a massive pipe organ or a really heavy bass drop at a concert that rattles your chest.
Oh, I know that feeling. It is more physical than auditory. But why are the whales here?
Because for them, it is not just a feeling, it is long-distance calling. Take a look at the text there regarding elephants. On the dry African savanna, elephants use these low rumbles around 15 Hz to talk to each other over an area of 30 square kilometers.
30 square kilometers? That is like shouting across an entire city.
And that is just in the air. In the water, it is even more impressive. Sound travels much more efficiently in water. Those blue whales in the image? They produce powerful infrasonic calls that can be heard by other whales over thousands of kilometers.
Wait, thousands? So a whale in the Atlantic could potentially hear a friend halfway across the ocean?
Precisely. It is like a global chat room built into the ocean. But we do not just study animals with this. We use it to protect ourselves too.
Protect ourselves? How?
See that note about meteors? When a large space rock hits our atmosphere, it creates a massive infrasonic boom. It is silent to us, but not to our equipment.
Like a silent alarm?
Exactly. Places like the Los Alamos National Laboratory have arrays of special microphones listening 24/7. They detect about 10 large objects, 2 meters or wider, entering the atmosphere every single year.
Wow. So while we are oblivious, the whales are chatting across oceans and scientists are listening to silent space rocks exploding.
The universe is very noisy, Sarah. We just need the right ears to hear it. Building on that idea.
I'm looking at this photo of the duck swimming, and the water ripples look uneven. Why are the waves in front so bunched up compared to the ones behind it?
That is the classic visual signature of the Doppler effect. Because the duck is moving forward, it's actually chasing its own ripples. It compresses the waves in front of it, shortening their wavelength.
Oh. And behind the duck, it's moving away from the ripples, so they get stretched out?
Precisely. Now, shift your eyes to the diagram of the red pickup truck below the duck. Imagine that truck is honking its horn while driving.
I know that sound. It starts high-pitched and then drops low as it passes you.
Exactly. Look at the sound waves in front of the truck. Just like with the duck, the moving source is squashing the airwaves together. The wavelength, or lambda, is getting shorter.
And looking at the equation here, v equals lambda times f, if the speed of sound v is constant.
You're getting it. The speed of sound in air stays constant, roughly 343 meters per second. It does not change just because the truck is moving.
So, if v is locked in, and the wavelength lambda gets smaller, then the frequency f has to get bigger?
Bingo! That is the mathematical reason why the truck sounds higher pitched as it approaches that lady standing on the sidewalk. Her ears are getting hit by waves more frequently.
But what about when the truck drives away?
Look behind the truck. The waves are stretched out. Wavelength increases. To keep our equation balanced, if lambda goes up, frequency must come down. That gives you that low, moaning pitch as the vehicle recedes.
The text here mentions galaxies and colors. Does this apply to light too?
It applies to all waves. If a galaxy is moving away from Earth, its light waves get stretched out. Since red is the color with the longest wavelength, we say the light is redshifted.
So we can tell a galaxy is running away from us just by checking if it looks a little too red?
Exactly. It is how we know the universe is expanding. From a duck on a pond to the edge of the cosmos, the physics remains the same. Now, check this out, we have finally arrived at the master equation. This single formula combines everything we know about moving cars, moving people, and shifting pitches.
It looks a little intimidating, Adam. You've got a massive fraction in the middle, plus, minus signs everywhere. It's a lot of algebra.
It is much simpler than it looks if we just decode the terms one by one. Look at the variable lowercase f on the far right. That is your source frequency.
So, in the exercise below, that would be the car horn blasting at 550 Hz?
Exactly. That is the true sound. Now, look at f prime on the left side. That is the heard frequency. That represents what the observer actually hears after the shift.
Okay, so the fraction in the middle is just the conversion factor?
Precisely. And the terms inside tell us how to convert it. We have three different speeds here. First, the plain letter V. That is the speed of sound. It's constant, usually 343 meters per second.
But then you have U0 and US.
U0, or UO, is the speed of the observer. That's the listener. And US is the speed of the source, the thing making the noise.
Okay, I see the exercise at the bottom. We have a car moving at 18 meters per second, and a bicyclist moving at 7.2 meters per second. Who is who?
The car is honking, so it's the source. The biker is listening, so they are the observer. Now, here is the trick for the math, look at the arrows. They are moving toward each other.
Right. When things get closer, the pitch gets higher. Like a race car zooming up.
Exactly. So to get a higher frequency f prime, we need to make that fraction bigger.
To make a fraction bigger, you make the numerator larger, or the denominator smaller.
Boom! That's why in the solution, you see them use the plus sign on top for the observer, and the minus sign on the bottom for the source.
Oh, I get it. Plus on top adds speed, minus on bottom shrinks the divider. Both make the final number huge.
You got it. That bumps the heard frequency all the way up to 590 Hz. Next segment. Let's examine this closely, because we are looking at how a theoretical physics equation actually saves lives in track storms.
You mean the colorful map in the bottom right corner? I see labels for Bloomington and Springfield, so that looks like a weather forecast.
Exactly right. That is a Doppler radar scan. Just like a police radar gun bounces radio waves off a speeding car to measure its velocity, weather stations bounce waves off precipitation.
So, instead of a car moving toward the police officer, it is rain clouds moving toward the radar station?
You nailed it. By analyzing how the frequency shifts, meteorologists can track the motion of the storm. Look at that scary red and hook-shaped area labeled hook echo. That specific rotation often signals a tornado is forming.
Wow, so the Doppler shift actually helps spot tornadoes. But what about the photo above it? That looks like a doctor's office, not a weather station.
That brings us to medicine. That technician is holding a transducer against a patient's arm. They are using ultrasound waves to look inside the body.
But what is moving inside the arm? The patient is lying still.
The patient is still, Sarah, but their blood is racing. The ultrasound beam bounces off millions of tiny red blood cells moving through the arteries.
Oh. So the blood cells are the moving source, just like the ambulance we talked about earlier?
Precisely. If the blood flows toward the transducer, the frequency shifts up. If it flows away, it shifts down. The computer color codes this information to create an image of blood flow speed and direction.
It is wild that the same math works for blood cells and storm clouds.
And for entire galaxies. Notice the text at the bottom regarding the red shift. When we look at distant stars, their light appears redder than it should be.
Red light has a lower frequency, right?
Correct. Lower frequency means the source is moving away from us. This red shift tells us that distant galaxies are speeding away from Earth, proving that the universe itself is expanding. This result is what we call Hubble's law.
From blood cells to the Big Bang. That is impressive.
Here is the key concept, and for once, it is not about velocity, frequency, or wavelength. It is about what is written right there in the vast blue sky. Your self-motivation will be the formula of success.
Oh, Dr. Adam. Look at those silhouettes. That is the moment every student dreams of. The caps flying in the air, the sun shining. It feels like a celebration.
It is a celebration. Think about the journey they have just completed. It was not a sprint, it was a marathon. We started way back at the beginning, struggling with basic units and dimensions.
I remember. Back when we were just learning how to measure the world. Then we stretched our minds with solids and elasticity.
Exactly. We dove deep into fluids, we turned up the heat with thermal physics, and we just finished listening to the intricate physics of sound waves. They have built a toolkit for understanding the entire universe.
And looking at this image, I see a bunch of relieved graduates throwing their mortarboards as high as they can. But knowing you, you probably see something else.
Well, strictly speaking, I see a classic case of projectile motion. Those caps are fighting gravity, Sarah.
I knew it. You never turn it off, do you? Even at the finish line, you are seeing physics.
I cannot help it. But look at the text again. Thank you. Enjoy physics, I hope. That is the most important variable in this equation.
Do you think they did? Enjoy it, I mean?
Physics is heavy. It is rigorous. But I hope they leave here with new eyes. I hope that the next time they hear a siren, or bridge a gap, or feel the wind, they do not just experience it, they understand it.
That is a beautiful thought. It is not just about passing a test. It is about staying curious.
Precisely. The slide says be motivated. That is the only force that overcomes the friction of life. We provided the textbook, but they provided the effort.
Well, this has been an incredible journey. Any final words for the class of Physics 101?
Just two. Thank you. Thank you for your curiosity and your hard work. Go out there, keep asking why, and let your own motivation be your formula for success.
Congratulations, everyone.
Class dismissed. Good luck.